All right. How's this volume level? Can you hear me in the back? Okay. A little soft. How's this? Too loud? Okay. I'm trying to get this right because I'm wearing it on my mask now, so it's going to be different. Let me know if it gets too loud, too soft, or anything like that. Okay. So we're going to get started today actually with a couple of slides that we didn't quite finish last time. Just wrapping up this dual formulation of the SVM. And then we'll get into kernels, which is our main topic for today. So I have a couple of slides that are not part of the slide deck that I posted. They're part of the previous slide deck. And they're just wrapping up this SVM dual formulation. So remember the part that we got to last time, I wrote a whole bunch of math on a slide, right? And the conclusion was that we can reach this final form for the dual formulation of the SVM, right? It looks something like this, where the objective, where you're maximizing over these dual variables alpha now, right, instead of your primal variables. And the objective looks something like this, where you have this linear term like alpha transpose 1, which is basically just the sum of all the alphas, right, written in vector form. And then this quadratic thing, alpha transpose Q alpha, for what I said last time, an appropriate matrix Q. And we'll get to that in a little bit. And then subject to some of these new constraints that we found, right, based on what we know about the optimal B and the optimal xi's, those primal variables. These constraints have to be satisfied by the alphas. What's kind of cool is that this is also a quadratic program, right? That was our goal last time, right? Was starting from the dual, try to reach an optimization problem that we know how to solve. We know how to solve QPs, and this is a QP because the objective is quadratic and the constraints are linear. So just like how we were solving, the original soft margin SVM constrained form, we can basically throw the same tools at this one. And then after solving this, we get a bunch of alpha stars, which is not actually directly what we want, right? We want the optimal parameters, right? And so we can recover the parameters according to, this derivation that we already worked out last time, that it's going to be a sum of the alpha I, y, I, x, I, where you replace the alpha with the alpha stars that you found. So previously, this was an optimization, when we had the primal formulation, right? We were doing an optimization on W, right? We were trying to do, arg min of W of, our thing. And then W was a d-dimensional vector, right? Because this is, a linear model with respect to x. And so if x is d-dimensional, then so is W. W also has to be d-dimensional. Now, what we have is an optimization problem on the n-dimensional, oh, that should be n-dimensional, capital N-dimensional alpha, right? So that's a little too thick. Let's rewrite that. Right, where n is the number of data points that we have, right? So whether you want to solve the primal or the dual also kind of comes down to which one of these things is larger. Do you have more data points, or do you have more features per data point, right? And you might be wondering, why would I have more features than data points? That seems really weird. We'll get to why that might actually be the case in today's lecture. But this is the general idea. And if you're interested, only if you're interested, okay, this is a topic that is oftentimes covered in this class. But I just think it's like so mathy and not really that relevant that I decided to totally skip over it. But if you're interested, there's something known as the KKT conditions, the Karush-Kuhn-Tucker conditions, which basically tell us why the solution that we get out of the primal or the dual formulations are optimal. They're basically, these conditions are satisfied for the SVM formulation that we found. Therefore, we can be assured that what we're actually getting out of this problem is the optimal set of parameters that we could ask for. But I'm not actually going to go into any of the mathematical details behind that because I don't think it's interesting. What I do think is kind of interesting is some of the intuition about these alphas, okay? So after we solve this dual problem, we get out these alpha stars. What do the alpha stars actually mean, Well, the alpha stars, there's one alpha for every data point, right? Alpha 1, alpha 2, all the way down to alpha n, right? And those alphas we know have to be within the range 0 to c, right? For, where c is like the, the hyperparameter that we set, right? Because that was one of the constraints that we found. So how do we interpret what that actually means? Well, as it turns out, and you can show this a little bit more rigorously, but I'll just give you the intuition. If alpha equals 0, okay, that means that the data point corresponding to that alpha is correctly classified and lies outside of the margin, okay? So it's, you can think of it sort of as like one of the easy data points, right? Where it basically, it doesn't really even matter all that much because it lies on the correct side of the hyperplane that you found and not within the margin that you had, okay? If you have alpha between 0 and c, these colors don't really mean anything. Red doesn't mean bad and green doesn't mean good. These are just different colors. If you have alpha between 0 and c, then what you have are points that lie on the margin. Okay, so they are correctly classified, but they're what we tend to think of as like support vectors, right? They're actually the ones that define what that margin is. And so, SVMs are all about maximizing that margin, and then it turns out that the points that define the margin, the support vectors, have this alpha between 0 and c. But what I said is not exactly correct because there is another type of support vector in soft margin SVMs, right? The other type of support vector are either the points that you get wrong or the points that at least lie within the margin. Okay, you also have those. And it turns out that for those, you're going to have alpha equal to c. Okay, so for example, this point over here is incorrectly classified. This point over here also incorrectly classified. Those are going to have alpha equal to c. Okay, so what's really interesting, oh wait, maybe I should. Right, so support vectors correspond to all indices I for which alpha I is greater than 0. What's really interesting about that is that in many, many cases, the support vectors are a very small fraction of the overall data points that you have. So if you have n data points, you might only have like, m support vectors where m is some way smaller number than n. What does that mean? It means you're going to have mostly alphas that are 0. And only some small number of alphas that are actually going to be greater than 0, some number between, greater than 0 to c, okay? And that's also really nice because like what we said before, right, our W star, right, is a sum over all the data points of alpha star I, yi, xi, right? But most of those alpha I stars are going to be 0. So they don't contribute into our sum at all. And we only have to care about the ones that are our support vectors, where the alphas are actually greater than 0. Okay, that wraps up the 2 slides that I didn't get to last time. Okay, let's get into today's main topic then, which is kernels. Today's an important lecture because what we're doing is we're finally returning to, if you remember in the very first lecture, on the very last slide, I had this question that was basically along the lines of machine learning, it's all about predicting y from x, but what is x, right? I don't know if that question made any sense to you back then. I don't know if it makes any sense to you now, but it is nonetheless an important question that we're going to have to think about a little bit. Okay, what is x? We haven't thought about it so far, really, because so far what we've done is really just use whatever x or, bold x, if we're talking about vectors, right? We're just using whatever x is provided to us. We assume that there's some set of features that's been collected, and then we take that and we just use it as is, right? And then what we've done so far is, given that, we've focused on devising different models for predicting y. That's what we've done so far, right? It's the x to y step. We haven't really thought so much about what is x in the first place. And what are those models that we've built so far? Things like, linear regression, logistic regression, SVMs, all of these models that we've built so far for predicting y from x, right? what is one thing that we know about everything that we've studied so far? Linear regression, logistic regression, SVMs, LDA, perceptron. What's similar about all of these models that we've seen? Yeah. There is an underlying distribution over where the data comes from, that's right, but can we be more specific? Like, what are we assuming about the distribution of y given x for the probabilistic models? Gaussian, sort of. It's a simpler answer. Yeah. Yeah, exactly. So all of these models are linear, right? Every single one that we've studied so far. They're either models for linear regression or they're models for linear models for classification, right? But what if your underlying relationship isn't linear? We haven't really talked about that problem at all, right? We've just assumed that, linear models are going to be good. Let's try to learn about all these different ones and apply them to our data sets. A lot of the times you're going to get data that's not, exhibiting some kind of linear relationship. It's very, very common, right? So then the question then becomes like, do these linear models still fit? And if they don't, what can we do? Well, as it turns out, that's a very related question to what is X? And then we're going to try to figure out how to answer both of those questions. And the overarching theme for how we're going to do this is basically to use the linear models that we've learned so far. So keep those tools, but put them on top of something that we call a feature representation. Okay, so instead of working with X, we're going to be working with some function phi that turns X into a different feature vector. Okay, and then we're going to hope that in this different feature representation, our linear models can work better if they weren't such a good fit in the original features X that we had. Okay, that's the idea behind what we're going to be doing for a lot of the rest of this course. And we're going to start that today with kernels. So I want to, have you recall this slide that we had at the end of the part of at the end when we were talking about linear regression, which is asking the question, how powerful are these linear models anyway? And what I said back then was that linear models by themselves might not seem all that useful, right? Because a lot of the times our data might exhibit a nonlinear relationship, in which case the linear model is no good. However, they can be quite useful. Linear models can be quite useful if we use the right set of features. And so what that means is that instead of using x directly, we're going to work with phi of x. Okay, I'm going to tell you in a sec what phi of x actually is. So this week, what we're going to do is we're going to discuss a fairly general approach to featurization that makes it possible to work with very large feature representations. Okay, so phi of x can turn x, which we say is like d-dimensional, into some vector that's way, way larger than d. In fact, we're going to see examples of how that feature vector can even be infinite dimensional. Okay, so we wouldn't ever even be able to write it down. Nevertheless, we can work with those types of featurizations, and we'll see how. And the general approach for how we do this is called kernelization. Okay, but to motivate it just a little bit more, I want to remind you of this, this thought exercise that we did also back in the linear regression part, right? And I'll go through this quickly because we've already seen this before, so hopefully it'll just jog your memory. Okay, remember we had, this example of maybe we have 2D data, so our original x is, x1, x2, and then we have examples that maybe look something like, have examples from one class that look like this, and then, examples from another class that maybe look like that. Well then, the decision boundary, right, the classifier that I really want to learn kind of looks something like this, right? This is the, just trying to draw a circle, close enough. This is the decision boundary that we would want to learn, and we can represent this. We know the equation of a circle, right, up to, some scaling and some shifting and stuff like that is something that looks like x1 squared plus x2 squared equals c, something like that, right? We probably need to shift over by like a and b or whatever, but just pretend that I did that also, right? This is what we want to learn, but this is a non-linear decision boundary, right? At least it is if I'm looking at, my original features, which might be something like, x1, x2, and maybe like a bias term if I decide to throw it in there, right? If these are my features, I can't learn this with a linear model, with any of the linear models that I've studied so far, that we've studied so far, right? This is going to be a nonlinear decision boundary if we use these original features, right? However, if I had some feature representation that was a little smarter and maybe tried to include, not just, these linear terms, but maybe also these quadratic terms, right? Like x1 squared, x1, x2, x2 squared, maybe also a bias term, why not? Well, then all of a sudden, if I use this feature representation phi of x instead of x directly, I can represent this with a linear model, right? If I learn a linear model on phi of x, it's able to represent, these types of decision boundaries if that's what I need for my problem. And then here's kind of an illustration of that idea that I think is, kind of neat. I don't think it exactly gets the right point across, but, as an intuitive thing, you can sort of think of it as like lifting your features into some higher dimensional space, right? Where in that higher dimensional space, there exists a linear boundary, a linear separating hyperplane that didn't exist in your original feature space. That's kind of the idea that we're going for here, right? So this is the intuition, yes. Yeah, so would phi of x also be able to do a regular linear boundary? Absolutely, right? Good question, because, if we wanted to, maybe the w that we learn only focuses on these dimensions and then just ignores, sets to 0, all of these quadratic dimensions, if that's what's needed, right? So if that was the best, then it might still learn something like that. However, we're going to have to define what best is, right? We're actually going to defer that to next week, but, having these higher featurizations might lead to what we call overfitting, right? Where, the model might not actually need those additional quadratic features, but it uses them anyway in order to do better on the training data, but then it suffers in generalization performance as a result. But we'll get into that in a lot more detail next week. Okay. So that's the idea, the motivation behind featurization. Now let's talk about why doing this naively might not be such a great idea. So suppose that my original input x is a d-dimensional vector. So on the last slide, just for simplicity, it was only 2-dimensional vectors, right? It was like x1 and x2. But in general, it could be x1, x2 all the way up to xd, right? What if I wanted to make a quadratic featurization of x for a d-dimensional x, like I did for the 2-dimensional thing on the previous slide? A quadratic featurization of x includes all of the original features, right? x1, x2 all the way up to xd, along with all of these pairs, xi, xj, right? So that's like d squared of those, right? And maybe a 1 if I choose to include it. This feature vector scales quadratically with d, right? If d gets larger, then my quadratic featurization grows, by, the square of that amount, however much it grew, right? In terms of both the space required to store all these feature vectors, as well as the amount of time it would take to actually compute anything of anything that I want to compute, like W transpose X or things like that, right? It would grow quadratically in terms of both time and space. And in general, if I wanted to use something that's not quadratic, let's say like cubic or quartic or, anything moving up to like the pth order, what we're going to have is d to the p time and space requirements. If you've never seen anything that looks like this, like big O notation, don't worry about it too much. It's basically just a way of saying I don't care too much about the constant factors that are lying in there. The meat of it is that, we're going to have scaling on the order of d to the p, right? Where d is the original dimensionality of my feature vector, and then p is the featurization, the polynomial order featurization that I want to use. Okay, so d squared for quadratic, but things like d cubed for cubic, or d to the 4th for quartic, and so on and so forth, right? And this is going to get pretty nasty really quickly if I have a large feature vector to begin with, for example, if d is large, and or I want to use a higher order polynomial, 4, 5, 6, these are all heard of, right? And so doing so naively is going to be a problem. And so what we're going to need is a better way to actually do this kind of featurization, and that's where kernelization kicks in. Okay? To figure out how we're going to do that, let's actually use the SVM dual formulation that we've already worked out as a concrete example and see if there's anything in there that we might be able to use to make things a little bit more tractable. We already saw this dual form, right? Now let me tell you what Q is, okay? Q takes the following form where the ijth entry of Q is going to be equal to this expression if I is not equal to j, or this expression, this much simpler expression, if it's, along the diagonal of Q, okay? It's a pretty interesting exercise to work this out for yourself, just based on the equations that we got to last time, right, at the very end of last lecture. But just for the purposes of today's lecture, let me just give them to you so that we can use them, okay? And remember, we also had that this, optimal weight vector W star is equal to this sum right here, right? Well, then let's think about for a second, like, what do we need to do when we see a new point x and we want to make a prediction for that point x? Is it +1 or -1, right? What are we going to be doing? We're going to be looking at the sign of W transpose x plus b, right, in order to make a prediction. So when I'm making that prediction, the real meat of it, what I really need to do is compute this W transpose x, right? And what is W star transpose x? It's this expression right here, right? If I just substitute in this original thing for W star, okay? There is one thing that we need to notice here, which is going to turn out to be quite important. And what we need to notice is that everything here actually depends only on inner products or dot products, if you like, between the x's. So we have, things that look like xi transpose xj, right? Or, xi transpose xi or xi transpose x, right? In the places where x shows up, right, they only show up as dot products and never as x's themselves, okay? And as it turns out, this is going to be quite important, but that's the high-level thing that we want to notice here. And we're going to try to figure out, is this interesting? And if so, why is this interesting? So let me reiterate a little bit. For the soft margin SVM, when we're in the training phase, when we're trying to find, all the alpha stars, right, what we're going to be doing is computing all of these xi transpose xj's, right, in order to form Q, right? That's what we need to do in order to make Q. And when we're classifying, so after we've learned, our classifier, right, after we've learned our alpha stars, when we're classifying a new point x, what we're going to be doing is computing xi transpose x, right, for all of my support vectors, for all of the xi's where alpha I star was greater than 0, right? Everything else we can sort of just get rid of, right? So we're doing all of these inner product or dot product computations during training and also during, testing, or when our model's making new predictions, right? If I wanted to do all of this, but I wanted to do it in some feature space instead of my original space, right, what would I be doing? Well, basically, I would just replace all of my x's with phi of x, right? So instead, I would be computing phi of xi transpose phi of xj, or phi of xi transpose phi of x, right, for training and for testing, respectively, okay? We're not actually talking about how to do this intelligently yet. We're just saying procedurally, this is what changes when I go from x to phi of x. It's just this right here, right? And like we said before, if we're working with large featurizations, like something that's, a high-order polynomial, right, then doing this naively can get really bad because now we're computing dot products between features that are much larger, right? And we had to construct those features in the first place, and now we have to do the dot product and everything. This is getting pretty nasty, right, if we're trying to use something like a high-order polynomial or something like that, right? But there's one key idea that's really going to save us here. And that key idea is that if you notice what we're doing, we actually never need phi of x directly, right? There's never anything that says, just give me phi of x, right? Or just figure out what phi of x is. The only thing that we ever do is actually compute these inner products between phi of x, right? And those are just numbers. Those are like, single number scalars, right? So if we found a way to maybe work with those scalars rather than trying to work with these really large feature vectors, right, then maybe we're on our way to doing something that's a little bit more tractable, that's going to scale better to the types of high-dimensional features that we might want to use. So can this bias anything? As it turns out, it can with something called the kernel trick, which is basically the key idea behind kernelization. Okay, so that's where we're trying to go. Okay, we want to work with these feature vectors, but they might be really hard to work with naively. We're going to have to figure out something a little bit smarter, and that thing that's a little bit smarter is the kernel trick, which I'll give you an example of on the next slide. Okay, here's a very dense slide, so get ready to write a lot of stuff. Let me give you an example based on the quadratic features that we've already seen. Okay, that's going to involve the least amount of writing, but it's still going to involve quite a bit of writing. So if I have quadratic, features for something like the two-dimensional x that we saw before, right? Just x1, x2, right? My phi of x looks something like, maybe we can put a 1 in front, and then the original features, and then all of these quadratic terms. Right? And, maybe I actually want this to be like a column vector instead of a row vector, so I like put a transpose there at the end, but who really cares? It's a one-dimensional thing. Just make it a column or a row or whatever you want, right? If I wanted to compute phi of x transpose phi of x prime for this quadratic featurization, right? Just like what I would need to do for the SVM, right? Well, what is that actually going to work out to? Well, phi of x looks like this. Phi of x prime looks exactly the same, except all of these are like the x primes, right? And I'm just doing a dot product, so it's like, each one of these multiplied with its counterpart in the other vector, and then all of that summed up, right? So I get something that looks like 1 plus, x1 prime, plus x2 prime, plus, x1 squared, x1 prime squared, plus x1, x2, x1 prime, x2 prime, plus x2 squared, x2 prime squared. Okay, everybody with me on that? That's just, the dot product between the vector that I already wrote out plus another copy of the vector for x prime. Okay? And so like I said before, this is scaling quadratically with how large x is, right? Here, if d is equal to 2, it's not so bad. If d is equal to 3, I would refuse to write this out because it would already be too long to fit on this slide, right? And it only gets worse from there, right? So for these small cases, it doesn't look that bad, but it gets pretty bad pretty quickly if we're doing it this naive way, okay? However, what I want you to do is I want you to consider the alternate expression, which is given by 1 plus x transpose x prime squared. Where did this expression come from? I don't know. Someone who was very smart, sat down and figured it out one day. But I'm going to tell you why this expression is so special. But first, what I want to point out is that there's no phi in here, right? This is just like the original x, right? There's no phi, which means that we're working in the original space, like the d-dimensional space, right? So we have nothing that's scaling like quadratically or whatever based on the featurization that we want to use. This is all in the original space, okay, which we assume is, small enough that we can do things efficiently, attractively, right? Well, what is 1 plus x transpose x prime squared? We can write this out a little bit, right? This is 1 plus, well, what's x transpose x prime? It's, x1, 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 x1 prime, right? Plus x2, x2 prime squared, right? I get this thing, which I can also write as like, just to make it a little bit more clear, just make 2 copies of it. Okay, and now in order to figure out this expression, I really need to do this like FOIL thing, but I have 3, right? So it's not just going to be FOIL, it's like, first, and then, all the middle terms and all this other random crap, right? So it's going to be like 9 things, right, that I'm going to write out. Right, so the first thing is we can look at 1 times this whole thing, which happens to be that thing. So I can just write that out, right? Plus, I'm going to leave myself some room for coefficients because I know that's coming later. x1, x1 prime plus, x2, x2 prime. That's what I get, right? And then I get, oh no, I get x1, x1 prime times this thing, right? So, just distribute x1, x1 prime to each one of these terms. What do I get? I get x1, x1 prime, right? So now I have 2 of these things, right? Plus x1 squared, x1 prime squared, plus x1, x1 prime, x2, x2 prime. Okay? And then the last thing, right, I'm sure everybody's bored out of their minds, is this thing times this whole thing, right? Which is x2, x2 prime, so now I have 2 of these, right? Plus x1, x1 prime, x2, x2 prime, so now I have 2 of these, plus x2 squared, x2 prime squared. Okay, cool. Is this cool? Maybe it is. Is this cool? Anybody tell me why it might be? Does it look familiar? Yeah, exactly. So this thing that I have here, very similar to this thing, right? I have some 2's that are poking out, but other than that, everything looks pretty much the same, right? So actually, what this turns out to be is it's also an inner product, a dot product, right? With features that are very similar to these quadratic features that I already defined, just with some root 2's thrown in, okay? Root 2's because I get these 2's popping out, right? Okay, so basically what I've done here is built a featurization, a quadratic featurization, right, without ever actually explicitly constructing that featurization, okay? So the key thing to note here, right, is that, I'm going to write it out just so everybody is on the same page. We didn't have to compute the features explicitly, right? I used this expression right here, right, 1 plus x transpose x prime squared, which operates in the original feature space, right, the d-dimensional feature space. And as it turns out, that expression corresponds to a quadratic featurization, Okay, it has, a couple of root 2's thrown in there, but we don't really care about those, right? What we care about is the fact that we get our quadratic features that we wanted. Okay, so this is the key idea behind the kernel trick. It's that there are certain featurizations, for example, quadratic, where we don't actually have to construct the quadratic features. We never actually have to construct phi of x. We just evaluate some other expression, which is easier to evaluate because it operates in the original space. Okay, so it takes up less time and it takes up less space, right? We just evaluate these expressions that, as it turns out, correspond to the featurizations that we wanted, at least the inner products of those, right? So if we have something like the SVM that only relies on these inner products, these dot products, right, then we can rely on the kernel trick in order to make it so that we never actually have to compute phi of x in the first place. We're just working with these alternate expressions that are going to evaluate to the same thing as the kernel, as the featurization that we wanted. Okay. There's a lot of words and also a lot of text. Yes.
How much do you have to worry about if your P is like greater, assuming you have more terms in the expansion?
Great. Yeah. Great question. Yeah. So what if we have something that's bigger than quadratic, right? So what if P is like 3 or 4 or 5, whatever it is that we want, 100, I will tell you this, but I won't actually prove it because it gets a lot more involved. We can replace this 2 with 3, 4, 5, 100, whatever we want, and that corresponds to that polynomial featurization. So in general, using polynomial features at least used to be, very popular because there was this really easy kernel evaluation that we could do to make it really much more efficient than using those features directly. Yes? Do the square root of 2's matter? Great question. So the answer is sort of, because they're going to change the eventual W that you learn, right? Like those features, or those dimensions of W will be scaled down by a factor of square root of 2 because your features are scaled up by a factor of square root of 2. But in the end, all that means is that it all just cancels out, right? So you don't lose or gain anything by having these different scalings. It just so corresponds to, slightly like a warped kind of thing, if that makes sense. Yeah. Okay, so let me try to generalize that example into kind of what the high-level idea is. So when we say the kernel trick, basically what we were saying is that for many useful featurizations, phi of x, right, we can compute inner products, phi of x transpose phi of x prime, without ever explicitly constructing phi of x itself, okay? So if we can work in our original d-dimensional feature space, but then implicitly be using these higher dimensional features, that's a big win, right? Because we allow ourselves to use linear models, right, in these higher dimensional feature spaces, but we don't have to pay the time or the space to actually be naively working in that higher dimensional feature space, okay? So this is a pretty key idea, is that if our model only relies on inner products like the SVM, right, which is part of the reason why the SVM is so cool, then we can do this kernel trick and allow ourselves much more modeling power, right? We're basically no longer restricted to only having linear hyperplanes or, linear boundaries. We can work with like quadratics if we just use a quadratic featurization, right? So that's the high-level idea. This kernel trick that we just discovered, it's really useful if the features that I want to use, like phi of x, if they're massive. Okay, so if I want to use a polynomial featurization with p equals 100, then doing this is going to be a huge gain. Like you can never naively do, 100 order polynomial features, but you can do it very easily just by using the kernel trick. In fact, we can even work with featurizations that are infinite dimensional, okay, which means that my features phi of x actually give me a vector that never ends. Okay, they just keep corresponding to more and more dimensions of my features. It might be kind of hard to understand what that's even doing. We'll talk a little bit more about that maybe at the end of this lecture, also next time when we get the chance. And again, this trick, it's only applicable if we have models that only require these inner products, right? 5x transpose 5x prime, and not the features 5x themselves. Okay, so we need to have these models, these formulations, that are amenable to the kernel trick, right? They use inner products and nothing else. And that's why we learned about the SVM dual formulation, because it's an example of a model. It's actually the canonical example of a model which can be kernelized, okay? If the SVM dual formulation didn't have this advantage, I never would have taught it to you in the first place, because other than that, it's just a bunch of math, right? It's not really all that interesting, but it's important because it can be kernelized, right? And the primal formulation was not going to be very easy to work with from this perspective. Okay, so that's why last Friday we talked about all this math. It's all coming, it's coming full circle now, in the sense that this is the main reason why the SVM dual is so interesting. Is it's going to be our first example of an easy to kernelize model. Okay, let's get into a little bit of the details. So when I say kernelizing a model, what I mean is, okay, that model only requires inner products, only requires dot products, okay? That is the prerequisite, right? If you have something that requires the x's themselves, then, you know, you're kind of out of luck because it's not going to be easy to apply these tricks that we just learned, right? But if I have a model like the soft margin SVM that only requires x transpose x prime, right? What I'm going to do in order to kernelize it is replace all of those x transpose x primes with phi of x transpose phi of x prime, okay? That's going to be the first step. Replace all of the x's with this alternate feature representation of x that we're working with, okay? But remember, what we're doing here is we're not actually explicitly representing these phi of x's, right? That's the thing that we're trying to avoid, right? So we want these inner products, but we're going to do so without ever actually looking at phi of x itself. How do we do that? What we have is what we call a kernel function, okay, k, which takes in two x's, so x and x prime, and then evaluates this dot product, okay, phi of x transpose phi of x prime. What is an example? K of x prime, x and x prime, if that equals 1 plus x transpose x prime squared, well, then that's the quadratic kernel that we've already seen, right? So we have some function that takes in two x's in their original d-dimensional form, right, and returns the dot product of those, of x and x prime, in the feature space that I want to be working with, okay? The kernel function, that's kind of, you know, the workhorse of this whole thing, right? That's what we really want to be doing. There's also a very common other, you know, object that we tend to work with during training, which is what we call the kernel matrix, this capital K, okay? The kernel matrix is an n by n matrix, okay, where n is the number of data points, and the ijth entry inside my kernel matrix is just my kernel function evaluated for those two training points, for xi and xj, okay? And so a lot of the times what we'll do when we're working with a kernelized version of a model is we'll just pre-compute this kernel matrix. Okay, so loop through all of my training data and compute all of the entries of Kij. And so like we've already seen, the soft margin SVM, okay, at least the dual formulation, is our first example of a model which can be kernelized, okay? Which meant that I only had these inner products, x transpose x prime. I was able to replace them all with phi of x transpose phi of x prime, and then I don't actually have to compute the phi's directly, right? I will instead be working with this kernel function and this kernel matrix in order to do what I want to do. And next time, we're going to see a couple more examples of other types of models that we've already studied that can also be kernelized. So the kernelized soft margin SVM, sometimes people just call this the kernel SVM, right, is as follows. We have this exact same thing that we had before. It's the same, the same optimization problem, right? But the Qs are now given by these expressions that are based on the kernel matrix, right? So before, what did we have here? Before we had xi transpose xj, right? And before here we had xi transpose xi. We have replaced those with phi of x transpose phi of xi transpose phi of xj, and that's just given by the ijth entry in this kernel matrix which we've pre-computed, right? So that's what happens when we do, kernelization of the SVM during training. And then for a new point, right, what we're doing is we're going to be computing something very similar to what we had before, right? What we had before is instead of this, right, we had xi transpose x. But now when I want phi of xi transpose phi of x, right, I replace that with a call to my kernel function k. So it's going to be k of xi and x, okay? And again, note that most of my alpha I stars are 0 for anything that's not a support vector, right? So I only have to make as many calls to this kernel function as there are number of support vectors, in my model. And so that's also quite nice. And I get to do this, in the original d-dimensional space rather than in whatever massive dimensional space that I'm trying to work in, okay? So doing this, right, this approach is going to be better than the primal formulation. Remember, what's the primal formulation? It's the one where we're doing argmin of w, right? W is a vector that's equal to the number of features that I have, right, which used to be d, but now it can be something much larger if I want to work with a larger featurization, right, d squared, right, or something like that. This approach that we have here is going to be better than the primal formulation if the number of features starts dominating. And remember, we said, why would that ever be the case? Why would we ever have number of features greater than number of data points? Well, the answer is you might have that at least implicitly if you start using these featurizations, right? If you start using a quadratic featurization of your original data, or a cubic, or something even much larger, right? So for an order p polynomial kernel, right, if you have d to the p much larger than your number of data points n, right, so these two arrows means much larger than, right, then it makes a lot of sense to be using this kernelized version of the dual rather than trying to solve the primal, which would operate in the primal, right, would operate in this space. The dual operates in this space. And so basically you kind of want to pick whichever one is smaller and then use the corresponding formulation. That's going to save you a lot of time and compute, right? That's the high level idea here. And so let's round this out with a couple of examples of kernel functions and their corresponding featurizations. So we've discussed an example of this already, but we have something called the polynomial kernel, which is kind of a generalization, right? Which is C plus X transpose X prime to the pth power, okay? What that corresponds to is a featurization phi of X that contains all combinations of P or fewer dimensions of X. So, like X1 to the P, X1 to the P minus 1 times X2, X1, X2, X3, all the way up to XP, like all of these P-dimensional combinations of different feature dimensions, right? And specifically, we already worked this out for the quadratic kernel where P is just equal to 2, right? And also we set C equal to 1. C is actually oftentimes what we call a hyperparameter, which we might be able to choose on our own, but it's not that uncommon to just set it equal to 1 and not worry about it. But this is an example of a very common kernel that people use, and as P gets large, right, 5, 6, 7, 100, 1,000, whatever, then you're really going to be wanting to work with a kernelized version of an algorithm rather than the original algorithm itself, right, because you're saving a lot of time and space that way. There's another kernel called the radial basis function kernel, the RBF kernel, also called the Gaussian kernel, where the kernel function k of x and x prime looks something like this. You might say, well, that looks a whole lot like the expression of a PDF of a Gaussian, and you are correct, and we'll see exactly what that means later. But actually, what's kind of cool about this is it corresponds to a featurization phi of x that's actually infinite dimensional, okay? And you're going to see exactly why this is in, I think, some later homework, which will actually have you exploring this particular property of the RBF kernel. And there are a ton of other kernels, too. You can look them all up. But these two, the polynomial and the RBF, are really the ones that are used in like 95% or more of the situations that people usually have. So we can just focus on these. Okay, so that's everything for today. Thank you.